So in this video, I will talk about two very nice complex analysis problems. Both of them are really basic. I mean, the question looks a bit weird, but like to solve this, you just need to have some basic tools of complex analysis. And so any basic complex analysis method basically comes from the Cauchy's integral formula, and eventually all of the theorems like there are like you have Liouville's theorem, or you have maximum modulus, or some other theorems like Rouché's theorem or argument principle. Everything basically comes from the one way or the other. Everything comes from the Cauchy integral. So yeah, we'll see. So the first question is: suppose f is an entire function that is from C to C, holomorphic, which is basically an entire function, and f is also 1 to. Then what is it? I mean, what is it? I mean, what can you say about it? Like, is there any special form of it? So let's see how we can do it. So first thing, uh, let's see how it's an entire function and it's one to one. So if it is a polynomial, then there cannot be more than one distinct factor because otherwise it will pick up two distinct roots. Meaning there are two elements distinct that goes to zero, but because it is injective, that will not be the case. So if is polynomial, then it has to be of this form, right? Where k is at least 1. And now if say k is bigger than 1, that means it will have some, is it perfect to at least. So if k is at least 2, then it will be of this form. But again the same problem will arise because if you take say this function say assume some value, let's call it zeta. Then again for zeta it will have two pre-images, right? Because it's a square root. So az plus b will become plus or minus square root of zeta, right? And again, you see there's a problem because there are two values going to same value. So two pre-images. That's again not possible. So k has to be 1. So if it is a polynomial, it's better be linear. And a of course cannot be 0, otherwise become constants. And now let's see. So this is if is polynomial. And there is a criteria that if is a polynomial, if and only if or infinity is a pole, right? By polynomial, I mean non-constant, of course. And you know what is infinity is a pole means? You have this function as the pole at origin, right? So now, so if infinity is a pole, we are done. We get a particular special form of it. Now, what if infinity is not a pole? That means the only option left is it has to be a removable singular. Sorry, it has to be an essential singular. So why infinity can't be a removable singular? So it's an easy question. Maybe you can think about it. Int is Liouville. So infinity is an essential singularity if it is not a pole. So we are at this situation. And so by Cassidy-Weierstrass, if you pick any neighborhood of infinity, the image will be dense. right? So for any, and by neighborhood of infinity, I mean sets of this form. Yes. So f of this thing is dense, meaning it has to intersect every open ball inside C, right? And now what you can do is, uh, so let's see now, uh, let's take this set. This is an open set. So by open mapping theorem, you know this set entire thing, it has to be open. And now this is dense, so these two sets must intersect. Let's call it U1, let's call it U2. So U1 intersect U2 has to be non-empty. And what does it mean? It means there is, say the, so zeta is in the intersection. Then zeta will be some f of z1 and also f of z2, where mod of z1 is less than r and mod of z2 is strictly greater than. But again, there's a problem, you see, because there are two distinct images. No way that, like, there is no way z1 and z2 cannot be, can be same, because they are in complete complement of each other, complementary. So uh, so the thing is, again, f is not 1 1 in this case, so there's a problem. And the problem started because we assumed infinity is an essential element. So this means infinity is a pole, because that's the only option left, right? And this means f is polynomial, hence linear. So if you give me any injective entire function, you have to give me a linear, as simple as that. So that's a very nice question. And you see that, like, in real analysis, things can be really weird. There are 1 1 functions from R to R, which is differentiable, but say for example exponential, right? Or any, say, x power or any a power is a positive. These are all linear injective maps, right? But then, and these are all real differentiable. But again, you cannot say anything because they are far from polynomial. So see, uh, complex analysis is pretty weird. I mean, real analysis is actually pretty weird. Complex analysis is a lot simple. So, and everything boils down to these one or two facts about open mapping theorem or Liouville's theorem. This is the main key part in most of the things that I've come across. Liouville's theorem and open mapping theorem, stuff like that, are making complex analysis a lot more simpler compared to what real analysis is pretty weird. So that's one of the question. Now the second question is, so again you were starting with uh, two entire functions this time, and you were given that their composition is a polynomial. Then again the question is, what can you say about individual? So again, everything boils down to those one or two facts. So let's see how we can do it. There are one or two ways to do it, but I think this like I found this way pretty easy compared to the otherwise. So you have the composition is a polynomial. So let's just denote the composition H. So H has a pole at infinity, right? Because it's a polynomial. And again, let's assume they are non-constant, otherwise it's become trivial. So again, there are only two possibilities for G at infinity. Either it's a pole, in which case G becomes a polynomial, and another case is it's an essential singularity. If infinity is an essential singularity for G, this means every set of this form, if you take the image of G, on this set, this becomes dense again by Casaretti response, right? So now let's see. And remember, each has a pole at infinity. So there would be at least one neighborhood of infinity. And by neighborhood of infinity, I mean sets of this one. These are my neighborhood of infinity. So there would be at least one neighborhood of infinity on which if you evaluate the age, the image will be, say, uh, so there exists some R such that this, if you will take the image of this thing, this will again be a neighborhood of infinity, right? Because at infinity, the pole means what? If you approach towards infinity, like if you take as big modulus of values of complex numbers, then the image will be like the image will again approach infinity, right? This means it will miss some small neighborhood around zero. You can imagine like that. So maybe you can imagine like this set, the image will be under age. So this is my some small circle. So the image will be something like that. And these type of sets cannot be dense because it's missing this whole portion of the interior. So it cannot be dense. Uh, so now let's call this R naught to be very specific. And so if you take this neighborhood of infinity and put G on it, this will be dense, right? Because G has an essential singularity at infinity. So this is dense. And now it's trivial because if you again apply F to it, it will again be dense, right? Because it's an image of a dense set. But this is same as H, and which is a problem because this image is missing this chunk of the complex plane. So this is a problem. So G better be a polynomial. Pole for G, hence a polynomial. So you get that this one is a polynomial. Now the question becomes a lot simpler. What can you say about F? And you may already assume, I mean, you may already can imagine that F has to be a polynomial as well. And why so? Let's think about it for a while. So say you can take up, say, there are a few ways to do it. And the first intuition should be like, if you take a power series of F, if it's a polynomial, it has to eventually terminate. But if it's non-terminating, that means it has larger and larger powers of Z. And inside you already have G. So let's take G to be something like that because it's a polynomial, we've already shown. And if you again put F on it and take a power series expansion, so the first term will be say let's say the power series expansion of F looks like this. The first term will be the constant term. And the second term will be F1 times the all of this inside. Right. Now the second term will be F2 times all of these things for this. So as you see, the terms are getting bigger, the powers are getting bigger and bigger. But this has to be a polynomial, right? So this has to eventually terminate, and which is not the case unless F itself is a polynomial, in which case the power series term. This is a bit intuitive, not very much concrete. So let's see how we can do it. Basically, the idea is again the same. If it has an essential singularity at infinity, if infinity is an essential singularity for F, then you get that every neighborhood of infinity, if you evaluate it will give me a dense set in C. But again, let's pick this neighborhood. Let's just denote this neighborhood by say U infinity R naught. So yeah, And because G is a polynomial, if you evaluate G on this U infinity R naught, this will again gives a neighborhood of infinity, right? Because G itself is a polynomial. So as you take sets of, say, as you take neighborhoods of infinity and you apply G on it, it will again give you another neighborhood of infinity because it has a pole as Z grows to infinity, right? And because F is having an essential singularity at infinity, this particular and remember this is an open set by open map. So if you take this neighborhood of infinity and apply F to it, this will give a dense set, right? But again, the problem, as you can already see, this. And we started with a particular neighborhood such that each of these thing is not dense. So yeah, again we are done because there's a problem. So F has to be a polynomial. Right. So again, you see how beautiful complex analysis is. If you are having two entire functions and you know their composition is say a polynomial, then they both has to be polynomial. And one thing you can also remark that if you combine both of the problems, so suppose you are having two entire functions f and g such that the composition is injective, right? So that means the composition of them are the composition is a polynomial. So each of them has to be a polynomial. And now because the composition is having degree just one because it's an injective function, then you can let me put this question: if fg holomorphic on C, that's an entire function, such that if compose G is 1, this means linear, right? And this means in particular it's a polynomial. So if is polynomial plus G is polynomial. And if compose G has degree 1, right? So what can you say about say if and G? For sure they're polynomial, but can you say anything more? So you can also always you can also think about this question for now. So let me stop it now.